Stand on a beach and watch the waves roll in. Each wave seems to come from somewhere beyond the horizon, from a place you cannot see. Now imagine standing at the edge of the entire universe, watching the fabric of reality itself stretch away into… What? This is perhaps humanity's most profound question, one that sits at the uncomfortable intersection of physics, philosophy, and the limits of human comprehension. The question, what is behind the universe, assumes there is a behind to begin with. But this assumption itself may be our first mistake, a trap set by our evolved minds that are designed to navigate three-dimensional space and linear time, not to grasp the true nature of cosmic reality. Our brains are pattern recognition machines, honed by millions of years of evolution to understand predators in the grass and fruits on trees, not the fundamental nature of existence itself. Yet here we are, asking the question anyway. It's a testament to the peculiar trajectory of human evolution that a species of hairless apes has developed the cognitive tools to contemplate the edges of reality. We've come a long way from wondering what lies beyond the next hill to wondering what lies beyond existence itself. The boundary problem: where does the universe end? Before we can ask what lies beyond the universe, we must first understand what we mean by the universe itself. Modern cosmology tells us that our universe began approximately 13.8 billion years ago in an event we call the Big Bang, but this name is misleading, a relic of a time when scientists were still grasping for metaphors to describe the indescribable. The Big Bang was not an explosion in space. It was an explosion of space itself, an expansion of the very fabric of reality from an infinitesimally small point. Imagine trying to explain to someone from the Middle Ages what a computer is. You might start with metaphors. It's like a very fast abacus. It's like a mechanical brain. It's like a book that can rewrite itself. But ultimately, all these metaphors fail to capture what a computer truly is. In the same way, when we talk about the Big Bang, we're using the limited vocabulary of spatial expansion to describe something far stranger: the origin of space itself. Since that moment, the universe has been expanding. But expanding into what? This is where our intuition fails us catastrophically. We imagine the universe as a balloon inflating into a room, with empty space beyond the balloon's surface. But cosmologists tell us there is no room. The universe is not expanding into anything. Space itself is expanding, carrying galaxies along with it, like raisins in rising bread dough. Think about it this way. If you ask an astronomer where the center of the universe is, they'll tell you it's everywhere and nowhere. Every point in space was, in some sense, the location of the Big Bang. The expansion isn't happening from a central point outward, it's happening everywhere simultaneously. Distance itself is being created as the universe expands. The observable universe has a boundary of sorts, but it's not a wall or an edge in any conventional sense. It's a horizon defined by the speed of light and the age of the universe. Light from regions more than about 46.5 billion light-years away has not had time to reach us yet, not because those regions don't exist, but because the expansion of space has carried them beyond our observational reach. This cosmic horizon is like standing in a vast fog where you can only see a certain distance in any direction, even though the landscape continues beyond what you can perceive. But here's where it gets even stranger. That horizon is different for every observer in the universe. An alien civilization in a galaxy 10 billion light-years away would have their own cosmic horizon, overlapping with ours but not identical. The observable universe is, in a very real sense, observer-dependent. Reality itself has a subjective component built into its very structure. The shape of everything. One crucial question in understanding what might lie beyond the universe is understanding the shape of the universe itself. Is it flat, curved, or something else entirely? General relativity tells us that mass and energy curve spacetime, and observations of the cosmic microwave background radiation suggest that on the largest scales, the universe is remarkably flat. But flat doesn't necessarily mean infinite. A flat universe could be infinite in extent, stretching on forever in all directions. Or it could be finite, but unbounded, like the surface of a torus, a donut shape, where you could travel in a straight line and eventually return to your starting point. These are called different topologies, and they have profound implications for what beyond the universe could mean. If the universe is infinite, then in a sense, there is no beyond. It's all universe, forever. Every possible configuration of matter and energy that could exist does exist somewhere, infinitely far away. There are infinite copies of you reading this text, some identical down to the quantum level, others differing in small or large ways. This isn't science fiction. It's a genuine consequence of an infinite universe with quantum mechanics. But if the universe is finite, then we can meaningfully ask, what is it finite within? What is the space in which this finite universe exists? Or is this question, too, based on a flawed assumption? The multiverse hypothesis. Universe beyond universe. One of the most compelling answers to what lies beyond our universe comes from the concept of the multiverse. This idea suggests that our universe is just one of countless others, each potentially with different physical laws, constants, and dimensions. But the multiverse isn't a single concept. It's actually several different ideas that come from different areas of physics. The multiverse concept emerges from several different areas of modern physics. Eternal. Inflation theory suggests that our universe is just one bubble in an eternally inflating cosmic foam, where new universes constantly spawn from quantum fluctuations. Each bubble universe could have different properties, different values for fundamental constants, like the strength of gravity or the mass of the electron. Imagine a pot of boiling water, with bubbles constantly forming and expanding. Our entire universe, with its 13.8 billion years of history, its hundreds of billions of galaxies, its trillions of stars, would be just one of these bubbles in an eternally boiling cosmic pot. The water is the inflating quantum field, and each bubble is a separate universe with its own Big Bang, its own space and time. The inflationary multiverse has a peculiar property. It's eternal into the future, and possibly into the past as well. Inflation, once started, never completely stops. It ends in some regions, creating bubble universes like ours, but continues in others, always spawning new bubbles. It's a universe-generating machine that runs forever. String theory, which attempts to unify quantum mechanics and general relativity, suggests the existence of perhaps 10,500 different possible universes, each corresponding to a different way that extra-spatial dimensions could be arranged. This number is so large that it defies comprehension. If you wrote it out, it would be a 1 followed by 500 zeros. For comparison, the number of atoms in the observable universe is estimated to be around 1080. In this landscape of possibilities, our universe is merely one point in an inconceivably vast space of potential realities. Most of these possible universes would be utterly inhospitable to life as we know it. The laws of physics might not allow stable atoms to form, or gravity might be so strong that everything collapses into black holes immediately, or so weak that structures never form at all. This leads to a controversial idea called the anthropic principle. We observe the universe we do because we couldn't exist in most of the other possible universes. It's a form of cosmic survivor bias. We're not in a universe fine-tuned for life. We're in one of the rare universes where life is possible, and that's why we're here to observe it. The many worlds interpretation of quantum mechanics offers yet another kind of multiverse. Every time a quantum event occurs with multiple possible outcomes, the universe splits into separate branches, each realizing a different outcome. In this view, there are countless parallel universes where different versions of history have unfolded, where you made different choices, where dinosaurs never went extinct, where stars never formed. This interpretation, proposed by physicist Hugh Everett in 1957, was initially dismissed as too outlandish, but it's now taken seriously by many physicists because it solves several problems in quantum mechanics without adding any new assumptions beyond the basic equations. The weirdness of quantum mechanics, the fact that particles seem to be in multiple states at once until observed, isn't weird at all if all the possibilities actually happen in different branches of reality. But here's the challenge that haunts all multiverse theories. If these other universes are truly separate from ours, if no information or influence can pass between them and us, are they real in any meaningful sense? Or are they just mathematical abstractions, elegant solutions to equations that have no physical existence? The philosopher Karl Popper argued that a theory that cannot be falsified isn't really scientific. By this standard, most multiverse theories are in trouble because, by definition, we cannot observe other universes. But many physicists counter that the multiverse emerges naturally from theories that are testable in other ways. If string theory or inflation theory makes predictions about our universe that turn out to be correct, and these theories also predict a multiverse, then we have indirect evidence for the multiverse even if we can't observe it directly. The nothing that is something. Perhaps the most unsettling possibility is that behind the universe there is nothing at all. But even this answer is more complex than it seems, because nothing itself is far stranger than most people realize. The concept of nothing has vexed philosophers for millennia. Parmenides argued in ancient Greece that nothing cannot exist, because to exist is to be something. This logical puzzle still echoes in modern physics. Quantum field theory tells us that empty space is not really empty. It seethes with virtual particles that pop in and out of existence, borrowing energy from the vacuum for brief moments before disappearing again, like guests who arrive at a party, interact briefly, and leave before anyone can get their names. These aren't just theoretical constructs. Virtual particles have measurable effects. The Casimir effect, first predicted in 1948 and measured in 1958, demonstrates this beautifully. If you place two uncharged metal plates very close together in a vacuum, they experience a force pushing them together. This happens because the quantum vacuum between the plates has slightly fewer virtual particles than the vacuum outside, creating a pressure difference. Empty space, it turns out, has pressure. The vacuum has structure, properties, and even temperature. In quantum physics, nothing is actually something, a state with definable characteristics and behaviors. Different quantum fields have different vacuum states, and transitions between these states can release enormous amounts of energy. Some physicists speculate that the Big Bang itself might have been triggered by such a vacuum transition. Some cosmologists, like Lawrence Krauss, have argued that the universe itself could have arisen from nothing through quantum fluctuations. In this view, there was no before the universe because time itself began with the Big Bang. Asking what came before time is like asking what's north of the North Pole, a question that seems meaningful but actually isn't. The key insight is that quantum mechanics allows for temporary violations of energy conservation through the Heisenberg uncertainty principle. A quantum fluctuation could briefly create a tiny universe, and if that universe immediately began inflating, it could borrow the energy needed for its expansion from its own gravitational field. The total energy of such a universe could be exactly zero, with the positive energy of matter and radiation perfectly balanced by the negative energy of gravity. But this raises deep philosophical questions. Is quantum mechanical nothing really nothing? Or is it already something, a framework of physical laws and possibilities that itself requires explanation? The philosopher Leibniz famously asked, "Why is there something rather than nothing?" If even the quantum vacuum is something, we haven't really answered his question. The deepest answer might be that true philosophical nothing, a complete absence of physical laws, quantum fields, space-time, or any structure whatsoever, is actually impossible. Perhaps existence is the only logically consistent state, and non-existence is the true impossibility. This would mean the universe exists not because something created it, but because its non-existence would be a logical contradiction. Beyond space and time. Our most fundamental theories of physics, general relativity, and quantum mechanics begin to break down at the smallest scales of space and time. At distances smaller than the Planck length, about 10^35 meters, and times shorter than the Planck time, about 10^43 seconds, the smooth fabric of spacetime predicted by general relativity becomes a roiling quantum foam where the very concepts of distance and duration lose their meaning. To understand how small the Planck length is, consider this. The Planck length is to an atom what an atom is to about 100 light-years. It's incomprehensibly tiny. At this scale, quantum fluctuations in space-time itself become significant. Space and time cease to be smooth and continuous, and become granular, foamy, and chaotic. This suggests that space and time themselves might not be fundamental features of reality, but rather emergent properties that arise from something more basic, like how wetness emerges from the collective behavior of water molecules even though individual molecules aren't wet. Some physicists speculate that spacetime might be like temperature, a large-scale phenomenon that emerges from the collective behavior of more fundamental entities. If space and time are emergent, then what lies behind them? What is the more fundamental substrate from which they arise? Some theories propose that the most basic level of reality consists of pure information or mathematical relationships. In this view, the physical universe we experience is like a computer simulation. not in the sense that someone programmed it, but in the sense that it is the physical manifestation of abstract computational or mathematical processes. Physicist John Wheeler coined the phrase "it from bit," suggesting that physical reality, it, emerges from information, bit. In this view, the fundamental constituents of reality aren't particles or fields, but bits of information, and the universe is essentially a vast information processing system. Every particle, every interaction, every event is fundamentally an exchange or transformation of information. This idea connects to holographic principles in physics. The holographic principle, inspired by black hole thermodynamics, suggests that all the information contained in a volume of space can be encoded on its boundary, like a 3D image encoded in a 2D hologram. Applied to the universe as a whole, this suggests that our three-dimensional reality might be a projection from a two-dimensional information structure at the cosmic boundary. It sounds like science fiction, but there's serious mathematics behind it. The ADS-CFT correspondence, discovered by Juan Maldacena in 1997, proves that certain types of quantum field theories in n dimensions are mathematically equivalent to theories of gravity in n1 dimensions. This suggests that dimension itself might be an emergent property, not a fundamental one. The simulation hypothesis. This brings us to one of the more provocative modern ideas, the simulation hypothesis, popularized by philosopher Nick Bostrom in 2003. The argument goes like this: if it's possible for advanced civilizations to create detailed simulations of universes with conscious beings inside them, and if such civilizations are likely to create many such simulations for scientific research, entertainment, or other purposes, then the number of simulated universes vastly outnumbers real ones. Statistically, we're more likely to be living in a simulation than in base reality. The logic is simple but unsettling. Imagine humanity survives another 1,000 years and develops the computing power to run detailed simulations of universes. We might run millions or billions of such simulations to study how civilizations develop, how physics works under different constants, or just for entertainment. If each simulation contains conscious beings who don't realize they're in a simulation, then for every one real universe, there are millions or billions of simulated ones. From a probabilistic standpoint, any given conscious observer is far more likely to be in a simulation than in base reality. It's like a lottery, where there's one winning ticket and a billion losing tickets. If you're holding a ticket, chances are it's a loser, even if you can't check it. If we are in a simulation, then what lies behind our universe is the computer hardware and the civilization running it, existing in some higher level of reality with potentially very different physical laws. That higher reality might have 7 spatial dimensions instead of 3, or time might flow differently, or the speed of light might be much faster or slower. The physical constants we observe might just be parameters set by the simulator, and that higher reality might itself be a simulation, leading to an infinite regress or to some ultimate base reality whose nature we cannot fathom. It's simulations all the way up, or at least until you reach a level where simulation is no longer possible or practical. Critics point out that the simulation hypothesis makes no testable predictions and might be unfalsifiable. If the simulators don't want us to know we're in a simulation, they can patch any glitches we discover. It's the ultimate conspiracy theory, immune to disproof. But some physicists have proposed ways we might detect signs of simulation. If the universe is being computed on a finite grid, like pixels on a screen, we might observe anomalies in the behavior of very high-energy particles. If the simulation is using certain computational shortcuts, we might see statistical patterns that wouldn't appear in a natural universe. So far, no such evidence has been found, but the search continues. The simulation hypothesis also raises profound philosophical questions. If we're in a simulation, are we real? Does our suffering matter? Do we have moral obligations? Most philosophers argue that even if we're simulated, our experiences are real to us. Our relationships matter, and ethics still apply. A simulated pain hurts just as much as a real one. The mathematical universe physicist Max Tegmark has proposed an even more radical idea, that the universe simply is mathematics. Not that the universe is described by mathematics, but that mathematics and physical reality are the same thing. In this view, our universe is one of many mathematical structures that exist in some abstract Platonic realm. Every consistent mathematical structure corresponds to a real universe somewhere in this landscape of possibilities. Tegmark's hypothesis starts from an observation. Physics keeps discovering that reality is deeply mathematical. The laws of physics can be written as elegant equations. The behavior of particles, the evolution of the cosmos, the warping of space-time, all follow mathematical rules. But maybe that's not because mathematics describes reality. Maybe it's because mathematics is reality. If a mathematical structure is complex enough, self-consistent, and contains structures that can process information, it might give rise to conscious observers. Those observers would perceive their mathematical universe as physical reality, never suspecting that they're essentially living inside an equation. This raises profound questions about the nature of existence itself. What does it mean for a mathematical structure to exist? Does the fact that we can write down equations describing a universe bring that universe into being in some sense? Or does existence require something more? Some spark of reality that mathematics alone cannot provide? Platonists in mathematics argue that mathematical objects exist independently of human minds. The number pi existed before humans discovered it, and would continue to exist even if all humans disappeared. The Pythagorean theorem was true before Pythagoras proved it. If mathematical objects exist in this Platonic sense, and if our universe is a mathematical object, then it exists in the same way. But this leads to strange conclusions. In Tegmark's mathematical universe, every logically consistent mathematical structure exists as a universe. There are universes with different numbers of dimensions, different laws of physics, even different kinds of logic. Some of these universes are simple, governed by a few equations. Others are incredibly complex, requiring vast mathematical frameworks to describe. And here's the really strange part. In an infinite space of mathematical possibilities, there are structures that look exactly like our universe up to this moment, but diverge in the next moment. There are mathematical structures where the laws of physics change tomorrow. There are structures where you're reading a slightly different version of this text. Every possibility exists somewhere in the mathematical multiverse, the cosmic consciousness. Some thinkers have suggested that consciousness itself might be fundamental to reality, not an emergent property of complex brains, but a basic feature of the universe like mass or charge. In this view, what lies behind the physical universe is mind, awareness, or experience. The universe exists because it is observed, or perhaps the universe is itself, a kind of cosmic consciousness observing itself. This idea has roots in both Eastern philosophy and in strange results from quantum mechanics, particularly the measurement problem. Quantum systems seem to exist in superpositions of multiple states until they are observed, at which point they collapse into a single definite state. The famous Schrödinger's cat thought experiment illustrates this. A cat in a box can be both alive and dead until you open the box and look. But what counts as an observation? Does it require consciousness? Some interpretations of quantum mechanics, like the von Neumann-Wigner interpretation, suggest that consciousness plays a special role in collapsing quantum superpositions. In this view, the universe remained in a quantum haze until the first conscious observers appeared, at which point reality crystallized into definite states. Most physicists are skeptical of such ideas, seeing them as misinterpretations of quantum mechanics. The modern consensus is that any interaction that creates a record, whether or not a conscious being observes it, causes quantum decoherence and effectively collapse the superposition. A camera or a rock can observe a quantum system just as well as a conscious mind can. But the hard problem of consciousness, the question of how subjective experience arises from physical process, remains one of philosophy's deepest mysteries. How does the firing of neurons in a brain give rise to the felt experience of redness, the taste of chocolate, the emotion of love? No amount of knowledge about brain processes seems to explain the existence of qualia, the subjective qualities of experience. Some philosophers and scientists, like David Chalmers and Giulio Tononi, propose that consciousness might be a fundamental feature of reality, not reducible to physical processes. Tononi's integrated information theory suggests that any system that integrates information has some degree of consciousness. By this measure, even simple systems might have tiny amounts of consciousness, while complex systems like brains have rich conscious experiences. If consciousness is fundamental, then perhaps the universe behind our physical reality is made of mind stuff, experience, or awareness. Physical matter might be what consciousness looks like from the outside, while consciousness is what matter feels like from the inside. This view, called panpsychism, has ancient roots but is gaining new attention from modern thinkers. Perhaps the most honest answer to the question, what is behind the universe, is simply, we don't know, and we may never know. There may be fundamental limits to what science can discover, not because of practical limitations in our technology or intelligence, but because of the structure of reality itself. The physicist John Wheeler suggested that the universe might be participatory, that observers and the observed are fundamentally entangled in such a way that it makes no sense to talk about a universe existing independently of observation. In this view, asking what the universe is when no one is looking is like asking about the sound of one hand clapping, a question designed to break our habitual patterns of thinking. There are also mathematical and logical limits to knowledge. Gödel's incompleteness theorems, proven in 1931, demonstrate that any sufficiently complex formal system contains true statements that cannot be proven within that system. If the universe is in some sense a mathematical or logical structure, there may be truths about it that are forever beyond our ability to prove or even comprehend. Some questions might be inherently undecidable. We might be able to construct multiple theories about what lies behind the universe, each internally consistent and compatible with all observations, but with no way to determine which is true. Science typically deals with this by appealing to Occam's razor, choosing the simplest explanation. But what if there are multiple equally simple explanations? There's also the problem of cosmic cognitive closure. Philosopher Colin McGinn has argued that just as a dog cannot understand quantum mechanics, no matter how hard it tries, there might be aspects of reality that human minds are simply not equipped to comprehend. Our brains, shaped by evolution to solve practical survival problems, might lack the cognitive architecture needed to grasp certain fundamental truths about the nature of existence. This is a humbling thought. We like to imagine that given enough time and intelligence, we can understand anything. But evolution doesn't optimize for truth-seeking. It optimizes for survival and reproduction. The fact that we've been able to understand as much as we have might be a happy accident, a side effect of intelligence that evolved for other purposes. There might be a ceiling to human understanding, and we might be approaching it.